This problem and all other CALC 152 problems can be found here at Sarai Studies. Link is in the description box below. The first thing you want to do is you want to let f of x be this, so you turn everywhere you see n to an x. At this point, we would check the conditions for the integral test using this function, but since we're told to use the integral test, I already know it's going to work, so I'm going to check the conditions at the end. Then you want to take the integral of this, that's what the integral test is, and then for the bounds, you just copy the ones that are here. So it would be 2 and then infinity. And then you would realize, oh wait, this is an improper integral because I can't just plug in infinity. So then you take the limit as some value goes to infinity and then plug that value in right there. And there you have it. Now this is just an improper integral problem you have to solve. And all you have to do is take the antiderivative of this. And you might try u sub and find out it doesn't work. And then you're going to try, oh, let me see if I can rewrite as multiplication like this and then do integration by parts with this being u and this being dv, and then you're going to be like, well, that doesn't work either. And then it's like you can't use trig sub, so it's like, what in the world is going to work? And then you're going to realize the derivative of tan inverse of x is equal to, I think of t as positive. It's always going to be x prime at the top and then 1 and x squared. We have this right here, and this to me looks very similar. The only thing that's different is this, but we can rewrite this as 1 plus e to the x squared. So now we have x here and then x prime there. And so essentially this here came from tan inverse of your x, which was e to the x. So the antiderivative of this is just tan inverse of e to the x, or arctangent, however you want to say it. That's being evaluated from 2 to b, and we're still taking the limit as b approaches infinity. Then you plug in, so tan inverse of that minus tan inverse of e to the 2. And then this really ends up as e to the infinity because b is approaching infinity, but then e to the infinity, that's still infinity. And so then you're looking at tan inverse of infinity, but you're taking the limit. So the second thing that you would have to have in your brain is the graph of tan inverse, or arctan, and know that the bounds are pi over 2 and negative pi over 2. And because we start at 2, then we're only ever looking from 2 forward. And then we're asking from 2 and onwards, as the x values of arctan approach infinity, as we go to infinity, what are the y values doing in arctan? They're going to pi over 2. So this here is pi over 2, and then minus, I'm just going to say arctan e to the 2. And because we got a constant answer, aka not infinity, then we can say that our original series converges by the integral test. That's assuming that it passes the conditions of an integral test, so we have to check those. Just note that on an exam, you would actually do this first, find out if you can do the integral test in the first place, and then actually perform the integral test. But since we know already that we need to do the integral test for this, I just go and get the answer and then check my conditions after. So here's how I remember the conditions. I write the word integral, and then the L, I write it like a cursive. I take the part that looks more like the L, like the normal L, like this part, and then I graph it, and then I ask myself, what is true about that graph? Well, number 1, it's positive because it's above the x-axis. Number 2, it's continuous because it's like continuous, it never stops, there's no holes, it's defined at every x value. And number 3, it's decreasing, it's literally going down. And so that's how I remember the conditions for the integral test. So then for the first 2 conditions, you really just have to write a sentence. If you remember, positive means that it's above the x-axis, meaning that for every x value that you put in, the y value is going to be positive. So you're really looking at, okay, we're starting at x is equal to 2. So if I plug in 2, I already know that e is like 2 point something. So the minimum it can be is e to the 2 over 1 plus e to the 4. So all of those numbers are positive. I don't have any negative numbers. So I already know that this is positive for all x greater than or equal to 2 because it's my bound. And notice I'm not saying e to the n or e to the 2n. We're checking the conditions of this. And finally, is it continuous? You just have to ask yourself, is it defined at every single x value? Because it's a fraction, I would really look at the denominator and ask myself, is there any way that this can be 0? Well, if the least we're going to put in is 2, the least it could be is 1 plus e to the 4, and that's not 0, so we're good. So we say it's continuous for all x's greater than or equal to 2. And finally, the last one, we have to prove that it's decreasing. What does it mean for a function to be decreasing? Well, if you have f of x that looks something like this, then your derivative f prime of x, because it's decreasing, is going to always be below the x-axis. So the derivative of your function should be negative if it's decreasing. In other words, we have to find the derivative of this and prove that it's negative. So this is just quotient rule. Quotient rule is f prime, g minus f g prime over g squared. So remember, this is f, this is g. So f prime is e to the x, and then g is 1 plus e to the 2x. And then we're doing minus f, which is e to the x. And then the derivative of this g prime, that's just chain rule, so that would be 2e to the 2x. And then over g squared, which is just this, 1 plus e to the 2x squared. Then to simplify this, this becomes e to the x plus e to the 3x, and then minus 2e to the 3x over here, and then over 1 plus e to the 2x squared. And then here we have 2e to the x, and here we have 1. So 2 minus 1, that's just going to end up being e to the 3x. It's going to be negative because the negative overpowers e to the x, and then we have over 1 plus e to the 2x squared. And you know that the least that can go in is 2. We already know that the denominator is always going to be positive because it's squared. And this is bigger than this. This is e to the 3x. So if we plug in 2 here, and we plug in 2 here, that's going to be bigger than just e to the 2 because it's e to the 2 times 3. And so that's bigger and it's negative, so the negative is going to overpower. So your numerator will always be negative, and since the denominator is squared, your denominator will always be positive. So overall, your derivative is always going to be negative. Then we can conclude that since the conditions of the integral test are true, and when we took the limit of the integral and we got a constant pi over 2 minus arctangent of e to the 2, then by the integral test, make sure you add that part, the series converges. Make sure you put that there. So that's it for this video. I'll see you in the next.